Hello, I'm Ali Ansari from Sharif University of Technology, and in this video, I will present our paper under the title of Divide and Conquer Frontend Bottleneck that will appear in the International Symposium on Computer Architecture in 2020. I've done this project under the supervision of my advisors, Pejman, Lotfi-Kamran, and Hamid Sarbazi-Azad. So let's get started. The front-end bottleneck is a well-known source of performance degradation in server processors. Several applications have very large instruction footprints that even exceed multi-megabytes. Moreover, recent work has shown that the instruction footprint is growing rapidly every year. On the other hand, the front end of the processors has limited capacity components. For example, the L1 instruction cache holds 512 instruction blocks, and the branch target buffer accommodates 2000 branch entries. Consequently, these components cannot capture the required entries and frequent L1 instruction cache and BTB misses hurt performance. To mitigate this problem, a myriad of instruction and BTB prefetchers are proposed. The simplest solution, the next line prefetcher, is used in the commodity processors. However, it remains a considerable fraction of misses uncovered. Consequently, more sophisticated proposals are suggested to tackle this problem. In this figure, we have shown Confluence and Shotgun that are state-of-the-art temporal and BTB-directed prefetchers. Nevertheless, the considerable storage cost as well as the considerable gap between the offered performance and the full potential shows that there is substantial room for improvement. Our goal is to reach here a solution for the front-end bottleneck that imposes almost negligible storage cost to the baseline design and at the same time offer the highest possible performance improvement. Prior work has tried to give a unified solution for the front-end bottleneck. In other words, a single algorithm is responsible for covering all types of misses. On the contrary, we will use a divide and conquer approach to solve this problem. We divide the front-end bottleneck into sequential, discontinuity, and BTB misses. Dividing the problem into smaller subproblems helps us to propose simple and accurate solutions for each type and avoid the complexities that can be seen in the prior work. Using this approach results in a proposal that outperforms the state-of-the-art prefetcher up to 16%. This is the outline of the content that will be given in this presentation. Till now, we had a brief introduction to the problem and our solution. We will have a simple motivation section followed by a comprehensive introduction of our proposal that is SM4L plus this plus BTB prefetcher. Then we introduce the methodology that is used to evaluate our proposal. We will show how our prefetcher works compared to the state-of-the-art techniques in the evaluation section. Finally, the conclusion section summarizes the content covered in this presentation. To use the divide and conquer approach, we separate the source of performance bottleneck in the core frontend to sequential, discontinuity, and BTB misses. To cover the sequential misses, sequential prefetchers are the common solution. The general idea is to prefetch some subsequent blocks ahead of the fetch stream. However, they cannot cover the discontinuity misses that occur because of branch instructions. Discontinuity prefetcher learns such discontinuities to cover these misses as well. Moreover, prior work has shown that how an instruction prefetcher can be extended to cover the BTB misses. It seems that combining these prefetchers can effectively cover all misses that downgrade the front-end's efficiency. However, in this presentation, we will show that the conventional implementation of these techniques has some fundamental shortcomings. Moreover, we will discuss how these shortcomings can be addressed to propose a powerful instruction and BTB prefetcher that considerably outperforms the state-of-the-art. We start with sequential misses. Sequential misses are those misses that are the subsequent blocks of the last demanded block. They contribute to from 65 to 80% of all misses, and hence they are frequent. Moreover, sequential prefetchers are a simple solution to cover these misses. For example, the next line prefetcher just prefetches the subsequent block whenever an instruction block is demanded. However, it has an important shortcoming, that is the timeliness. Prefetching a single block ahead of the demanded block cannot cover the large number of clock cycles required to fetch the block from the lower levels of the memory hierarchy that results in stall cycles and performance loss. Increasing the prefetch depth is the simplest way to improve timeliness. For example, the next 4-line prefetcher prefetches the 4 subsequent blocks when it is triggered. However, the solution results in lots of useless prefetches. The given pseudocode clarifies this. It contains 2 functions that are consecutively located in the memory. Assume that F1 is called and its execution starts with the evaluation of the if condition that is located in block A. Having a next 4-line prefetcher, blocks A plus 1, plus 2, plus 3, and plus 4 will be prefetched. Assuming that the if condition is true, the next 4-line prefetcher has correctly prefetched block A plus 1 that follows the instructions in the if body. However, blocks A plus 2 and A plus 3 are useless prefetches since the else body will not be executed. After the if body executed, the instructions at the end of this function will be executed that reside in block A plus 4. Fortunately, these instructions are timely prefetched when the next 4-line prefetcher was triggered on block A. However, accessing this block will trigger the next 4-line prefetcher to prefetch blocks A plus 5 to A plus 8. These blocks fall in the subsequent function F2 that is not necessarily called. Consequently, they will be useless prefetches that pollute the L1I cache. This example clearly shows how increasing the prefetch depth to obtain timeliness may result in issuing a large number of useless prefetches. But what happens if there was a smart sequential prefetcher that knows which sequential blocks should be prefetched? In this way, it can issue both timely and accurate prefetches. The key to building such a prefetcher is to exploit the locality among the instruction cache block sequences that are already used to build temporal prefetchers. In other words, if a prefetch was useful, it will be useful again and should be prefetched. Similarly, if a prefetch was useless, it will be useless again and it should be filtered. To have such a selective sequential prefetcher, the useful subsequent blocks should be highly predictable. This figure shows that the useful subsequent blocks of each instruction block are correctly predictable with about 90% accuracy. If the sequential prefetcher learns these patterns, it can simply use them to timely and accurately prefetch the useful sequential blocks. We try to teach the sequential prefetcher the useful sequential prefetch candidates, and accordingly, we propose the selective next 4-line prefetcher, or simply SM4L. To teach these patterns, we use a tagless and direct nav table named SecTable. Each instruction block is directly mapped to an entry of SecTable that is a single bit that indicates whether sequentially prefetching of that block will result in a useful or useless prefetch. We provide 16K entries for SecTable that requires only 2 kilobytes, that is a relatively small storage requirement. To exploit SM4's algorithm, consider this sequence of demanded blocks. When this sequence is demanded by the processor, SM4L finds an entry of SecTable that corresponds to block A and sets it. It means that block A is a useful one that should be sequentially prefetched. Similarly, the next entry is set that corresponds to block A plus 1. The subsequent entry is reset because block A plus 2 is not demanded. Consequently, SM4L will not prefetch A plus 2 since it considers it a useless prefetch. Similarly, the entries of sec table are updated and SM4L prefetcher uses this information to timely and accurately issue sequential prefetches. Covering the sequential misses, the remaining misses are discontinuities that a sequential prefetcher intrinsically cannot cover. For example, in this sequence, the control flow of the program is changed from block A plus 2 to B and from B plus 3 to C. Discontinuity prefetcher is a simple technique to cover such misses. However, conventional discontinuity prefetcher has some major shortcomings that limit its efficiency. First of all, discontinuity prefetcher uses a next for-line prefetcher to cover the sequential misses. Nevertheless, we have shown that the next for-line prefetcher imposes lots of useless prefetches. Moreover, it manages its metadata in a way that imposes considerable storage cost. Besides, discontinuity prefetcher uses a tagless table. In consequence, conflicts cannot be detected that may result in lots of wrong discontinuity prefetches. Finally, discontinuity prefetcher can prefetch up to a single discontinuity ahead of the fetch screen that provides a limited look ahead. Such limitations motivate us to propose an enhanced implementation of discontinuity prefetcher named DisPrefetcher that does not suffer from such shortcomings. The key point in designing this prefetcher is that discontinuities are the result of branch instructions execution. Consequently, by knowing the branch instruction, its target can be prefetched to eliminate discontinuity misses. While each instruction block can hold multiple branches, we found that most of the time there is a single branch inside of the block that causes discontinuity misses. Consequently, we record up to a single discontinuity per block to cover discontinuity misses. To know where the branch instruction is located inside the instruction block, we record the instruction offset of that branch instruction. Moreover, instead of recording the target address, we use a simple decoder to extract the target from the branch instruction. These policies help this prefetcher to have a very compact metadata record that imposes low storage cost to the design. This figure simply shows an overview of this prefetcher. It uses this table to hold this metadata that is partially tagged and URICNAT that is looked up by the block address. We empirically found that a 4-bit partial tag is good enough to have a good balance between the accuracy and the storage cost of this table. Consequently, each entry of this table contains a 4-bit partial tag and a 4-bit branch instruction offset. We have used a 4K entry this table requiring only 4 kilobytes. This figure elaborates on why we record a single discontinuity for each block. It shows that in about 80% of all discontinuities, the branch instruction that has caused the new discontinuity miss is the same as branch instruction that had caused the last discontinuity miss. Consequently, we record up to a single discontinuity for each block. Tracking multiple branches for each block may help to cover all the discontinuities at the cost of the considerable storage cost and a sophisticated logic. While SM4L tries to offer timely prefetches, in the presence of frequent discontinuities, SM4L's high look-ahead will not give a benefit. To effectively prefetch these cases, we propose a proactive sequential and discontinuity prefetcher. Suppose that block A is demanded. SM4L is triggered to prefetch A plus 1. When this prefetch candidate is determined, we consult this prefetcher to know whether this block has a discontinuity or not. This prefetcher finds 1 and prefetches B. Then SM4L checks the useful subsequent prefetch candidates for block B and prefetches B plus 2. Similarly, this determines that C is the target of discontinuity in block B plus 2 and prefetches it. SM4L does not find a useful sequential prefetch candidate for C. However, this prefetcher finds that D is a discontinuity prefetch candidate and prefetches it. Again, SM4L prefetches D plus 3 since it's a useful sequential prefetch candidate. Such a chain of prefetches can be endlessly created. It gives this opportunity to have a sufficient look ahead of the fetch stream as far as required. However, such a chain of prefetches should be terminated on a specific threshold to avoid issuing useless prefetches because of going far ahead in the fetch stream and entering the wrong path. Prior work has shown that having a powerful instruction prefetcher results in a powerful BTB. The main idea is to decode the fetched and prefetched instruction blocks to extract their branches and fill in the BTB. However, prior work has completely redesigned the BTB. Confluence has used Air BTB, and Shotgun divides BTB into 3 separate BTB structures. We argue that to have a powerful BTB, it is not required to completely redesign it. We use a confluence-like BTB prefetch buffer to hold the extracted branches and then remove the useful branches from the BTB prefetch buffer to the main BTB. In this way, BTB can remain untouched and just a simple small BTB prefetch buffer is added near the BTB. To evaluate our proposal, we have used Flex's full system simulator and tested our proposal on a wide range of benchmarks from different categories. The simulated processor is a 16-core CMB that each core has a 32 kilobyte 8-way set associative L1I cache and a 2K entry BTB. The branch predictor is Tage, and the last level cache has 32 megabyte capacity that is shared across the cores. This figure shows the obtained speedup with our proposal SM4L plus this plus BTB prefetcher compared to Confluence and Shotgun. Our proposal offers a 5% speedup compared to the competitors, and it can be seen that it outperforms them in almost all of the evaluated benchmarks. Moreover, the performance gap reaches 16% in OLTP DBA that has the largest footprint among these benchmarks. It clearly shows that our proposal can effectively prefetch for extremely large workloads, while some other proposals fall short of efficiency. Finally, we see that SM4L plus this plus BTB meets the goals. It requires a small storage budget to work effectively. Moreover, it offers considerable performance improvement compared to the state-of-the-art proposals. It has a simple design since it looks at 2 simple Greek math and tagless or partially tagged tables. Furthermore, the BTB structure has remained untouched, and it is not required to make such heavy and delicate changes on the front end of the processor by redesigning the BTB. There are some other details that are not covered in this presentation, such as why Shotgun cannot work effectively for large workloads and how we have extended our work to support variable length instruction set architectures. Moreover, we have explained the detailed implementation of the proactive sequential and discontinuity prefetching algorithm, and we have provided a detailed comparison of our proposal with Shotgun and Confluence. I would like to invite you to read our paper if you are interested in to know such details. At the end, I appreciate you because of watching this video, and I hope you enjoy our work. Most importantly, I hope you stay safe and healthy during this unwelcome pandemic, and it will be great to meet you in our live stream presentation that will be held on June 1st from 12 to 12:15 p.m. in Eastern Daylight Time. Please feel free to post your questions regarding this work in the forum, and I will really enjoy to answer your question and discuss this paper with you. Have a good time and goodbye.